So a weakness of the gradient descent method we found is that it has perpendicular search directions. So then in some situations it can take a long time to converge. So today I'm going to give two examples from a numerical code of gradient descent, one where it converges slowly because the function is elongated, and one where it converges quickly. I'll then provide the sort of solution to this, which is the so-called conjugate gradient method. And the conjugate bit means that we break this orthogonality of search directions. We allow subsequent search directions to be non-orthogonal. Okay, so this is a slide showing a numerical solution of the gradient descent method, something you'll look into more for your coursework too. And we've got a function here that's very elongated. So the contour lines are very spread out. The minimum is kind of in here. So that's the pen up. So our minimum is there. And then this is our starting point. And from last time we observed, and we actually proved as well, so we observed it in an example and we also proved that because the way gradient descent is constructed with a trajectory down the gradient and a minimization along it, successive search directions need to be perpendicular. And this example shows this weakness in great clarity. Because we've got a very elongated function, the gradient descent doesn't work that well. It takes many iterations, and look at it going, and the iterations get smaller. It is converging towards the solution, that's good. We will get to our minimum, but we seek a more efficient method. And this is where this conjugate gradient method, this word conjugate I will explain, comes to solve this problem of orthogonality. Okay. So that's a very elongated function, but if we just contrast that with sort of a very symmetric function here, so this is a very symmetric function. So the minimum this time is in the middle of these contours. Of course, we don't label the contours explicitly just for this common thing in this topic is just to draw the contours and assume that you know the minimum's in the middle and then somewhere, and then we're increasing. But of course the function does increase. You can see that the MATLAB here has color coded these functions, and this is the start. So these are actually perpendicular, and it actually gets to minimum in 2 steps. So what we want to do first today is quantify this symmetricalness, if you like, of the function using our Hessian matrix, and in order to know when the gradient descent will be a good method to use and when we might want to resort to something that's more efficient. So and by the way, there's a code associated with this that shows this, and it's worth looking at because coursework. So I'll post that on LE. We'll have all this inside, and you'll notice that in this code the minimization is done using a golden section search. So whilst we do an example by hand, by minimizing by hand, by differentiating with respect to alpha, our trajectory length, here minimization in the code is done by our golden section search, which is a nice combination of the sort of second part of this section of the module and the first part. So have a look at that and try and understand how it works. There's 2 choices in this: a symmetric, reasonably symmetric, and an elongated functions. And that's the ones that are the results that are shown in the lecture notes there. So the symmetric or near symmetric example is f of x of y equals 3x squared plus 4y squared. So another way of looking at it is the ellipticity of the function of the contours, basically. How much ellipses are they, or how close they are to circles. And we're just going to use our Hessian. Of course, you could look at the major and minor axes, but we're going to use the Hessian given we've calculated away. So Hessian, I'm just going to write it down because we've stated it several times now. Second derivative with respect to x gives us 6x and then 6. Second derivative with respect to y gives us 8y and then 8. And there's no xy term, so we get zeros on there. And so when actually a matrix is diagonal like that, this is trivial, very easy to figure out the eigenvalues. The eigenvalues are just the diagonal values. So the eigenvalues are simply 6 and 8. And what we're interested in is to quantify the symmetricalness. And it turns out the symmetricalness, that's a word, you get the idea though, is we can use the condition number. So this is a different use of the condition number. Before we had the condition number was the ratio, remember is this ratio, let's just write it down as a ratio between lambda max to lambda min. And we were using it in the past to understand how stable the inversion problem is. Here we're just going to use it to quantify how symmetrical the function is. So it's another use of that thing. So it's lambda max over lambda mix, which is 8 on 6, which is 4 on 3. So the condition number of H, our Hessian, is small or close to 1, i.e. close to 1. Therefore, F is symmetrical, or is very symmetrical. I'm using these terms quite qualitatively here, but get the idea. And thus, gradient descent converges quickly. In contrast, that function there. Okay, that's the 3x squared plus 3y squared function. In contrast, we just want to see the other function that we used, which was the was this drawn out function. So this function here. So in contrast, the long and thin function. So I'm trying to link a qualitative picture with a quantitative one here. You might have better words to describe it, but it was this one. So we had 3x squared minus 8xy plus 6y squared minus 2 of x. The Hessian then, in this case, so the second derivative with respect to x is 6, second derivative with respect to y is 12 now, and the cross bits are minus 8. And if we use MATLAB for this one, because the eigenfunctions are not simple numbers, you can take eig of h, and more importantly, you can do the condition number of h, or condition number of h, which takes you straight there. And the condition number of h is 38.5. So the condition number is a lot larger now, larger than that near symmetrical case, 38.5. Therefore, the gradient descent converges slowly. So the question is, how can we improve on these long and drawn out cases? So how can we improve on gradient descent? And the answer is to put this conjugate idea in front of it. So the question then is, what do I mean by conjugate? Well, it's all to do with breaking this orthogonality in gradient descent. Okay, gradient descent is still very useful, and it's used in data science examples. And the example you'll have next in question 2 of your coursework next term, as I understand, will be using a gradient descent, because it still has useful. It's a very simple algorithm to iterate. But now we want to see, what we want to see is how we can improve it. And let me just show you the picture of the end result of the conjugate gradient descent. Sometimes leave this as a surprise, but let's go straight there. So we're going to go back to our function that we looked at before, this quadratic function example where we minimize by hand, differentiating with alpha. So the gradient descent was so the gradient descent is in black. So we did 2 steps of gradient descent. That's the gradient descent. That's your gradient descent. But of course, we're limited by the fact that these directions are perpendicular. But what conjugate gradient descent tries to break that. So this is the conjugate direction in red there. And that's the basic. So that's what conjugacy means. It means constructing our directions but they're not perpendicular. The question is, how would you construct them in a more appropriate way? Well, the key is that we use the Hessian. So we're going to use the Hessian matrix now to break this conjugacy, and it's going to become a much more efficient way of converging. And in fact, the conjugate gradient, the gradient and conjugate method in this way share the first direction, but the second direction just takes you straight onto the minimum, in fact. So that's the big sort of punchline with the conjugate gradient method as far as we're concerned. So let's define this idea of conjugacy more precisely. Conjugate directions. So the best way to see this first time is just to see it in light of the gradient descent. So gradient descent search directions are orthogonal. And these search directions, remember, we're going to call SI and SJ in this case. So that means that the inner product dot product of Si and Sj is 0 for I not equal to j. Okay. Hopefully you're beyond just using dot products now and you're comfortable with using these S transpose S, the sort of inner product. This is the inner product, yeah. Because when you put something into leave a matrix, the sort of dot product utility of the dot product goes, and you need to sort of start using this notation of the dot product. So that's gradient descent. So conjugate gradients involve inserting H Hessian into the above. Now, this is not a random thing. The Hessian is the second derivatives of the function. It contains a lot of information about the shape of the function. So we can start to see actually we're putting extra information in here, whereas gradient descent is just blindly searching in perpendicular directions to the minimum. The H brings in all sorts of extra information about the shape. We know that if H is positive definite, i.e. has positive eigenvalues, then it's a convex function. So it actually is a very sensible thing to do. So we're going to now define conjugacy SI transpose, and we're just going to put our H matrix in the middle here. And this is a key. So rather than being restricted now to orthogonality, we've got a modification where the directions are conjugate to one another. Okay, so SI and SH are conjugate. Okay, so there's a little bit in the notes showing that actually you can do the conjugacy, you can reverse I and J indices if you want. Because H is a symmetric matrix. I'll just leave that as sort of background information if you want to look at that. What I really want to do now is just show an example of how this will work. So, e.g., so given an H matrix, keep an eye on the time. Yeah, I'll make this the last thing, and we'll continue in the next video. So we've done a second derivative of a function, and it's thrown out this Hessian, quite nice, convenient for our purposes. And of course, that's the Hessian of our original function we were starting with. Okay, so this is equation. This is the Hessian. Let me remind you what it is, because we've just been looking at two other functions of f of x of y equals 2x squared plus 2xy plus 2y squared minus 4x minus 6y. So this is the function we're going to be focusing on now. Okay, so let me just remind us this function here. Okay, so that's the function we originally started with, that Hessian, and it's got a minimum of a third and a 4/3, and we're sort of basically comparing with that. So let's just write that down again. Sorry, I've erased that now. No, H equals 4, 2, 2, 4. Okay, and our first search direction we need to get from another method, it's a little bit like other numerical methods where you start with a different method first, is we have to share it with gradient descent. And that was S1 is -1, 0. Okay, that was the one that was taking us from our starting position of 3, 0, and we're going in that direction. So we got a Hessian, we've got a first search direction. So now we can do a conjugacy. So our conjugate search direction, we're going to choose, we're going to call S2. So before, S2 was just done from the gradient, but now we're just calling it AB, and we're going to use our conjugacy to define the direction. So we have called S2 AB. Right, so the relevant conjugacy relationship then here is that S2 transpose H S1 is 0. Okay, so I can write it either way around because H is a symmetric matrix, and that's, as I said, that's demonstrated in the notes. So I'm basically going to do it this way around. So I've got my second search direction and my first direct search direction there. So we just fill that in. So we have the second search direction to AB. So it was a column vector, but we've transposed it. That's that bit there, goes to there. Then we have our Hessian matrix, which is 4, 2, 2, 4, just interleaving that. And then our first search direction, which is -1. Okay, so that one goes to there, that one goes to there, that one goes to there. Yeah. Right, and that's 0. Okay, so when you have these sort of inner product setups, the way to think about calculating is maybe the reverse direction of reading. So basically what you want to do is multiply this bit first, and then deal with multiplying it by AB. So all we've got then, so let me just get rid of that just for room. So all we got now is a simple, if we just basically forget about that for a little minute, just multiply through that, we've just got a simple matrix multiplication then. So given a vector, which is basically -4 at the top, because you multiply 4, 2 by -1, 0. And on the bottom you have -2, because you get from 2 down to -1. Okay, that should be, let's say, there. Pre-existing methods. And then, so then we've got this thing that we're just two vectors we're inner producting or dot producting together. So we just multiply A by -4, B by -2. That gives -4 times A minus 2B is 0. Okay, so that's the first bit. What you notice is we've got one equation and two unknowns. So we have to choose one of these constants. In a sense, that's fine, because all your conjugacy method is defining a direction for your new search direction. It's not defining it exact, its length as much such. All this relationship is just, so all we're doing is trying to break the orthogonality of directions. We're not so worried about the length. So what we might choose, we're going to choose one that's maybe sensible for a problem, but you can choose whatever you like for A, and then gives you B, and because you have this next section of minimization in the conjugate gradient method, it turns out it doesn't matter what you do choose for A, but I'm just going to choose A such that it gives a vector pointing in the direction. So we're going to choose A equals -1, but it's true that other values will still work after minimization stage, minimization on the trajectory. So all the conjugate gradient is very similar to the gradient descent apart from the directions you choose. So we're still going to choose a direction and minimize along the trajectory. All I'm going to do here is get that direction, and then in the next video we'll actually minimize along that new direction. So we choose A is -1, so the expression we had was -4A minus 2B is 0. We choose A is -1, and that implies that is 4. 2B equals 4, which implies B equals 2. So that's great. So A is -1, B is 2. So S2 now is in the direction -1, 2. And that's great because we now have a direction of S1 that goes along this direction, but S2 before in the gradient descent was going up the perpendicular direction, but now in conjugate gradient test we've got a direction that goes kind of like that, which is non-perpendicular, and that's going to be much more efficient. So we'll stop there, but next time we're going to then construct the trajectory along this direction S2, and then minimize along it and see what that gives us. Okay, so see you next time.